Okay. So what I want to talk about today is so we've done. I'm just gonna kind of keep track here. Can I do it? Yeah. All right. So we've done an observation. We got to talk about triangles for a moment, and I'll explain why. And then story from ancient Greece, and we got to talk about and then our project. So this is oh yeah. Good way. Okay, so this is what we're up to today. I have to write that down because otherwise I'm really good at forgetting stuff. And we have. I always forget. Does this class end at 11 or 10:55? 11. Okay, cool. Because we actually have a whole ton to talk about. So first, I want to remind you folks about some stuff that you may have seen in math class before. Some of you may be like, "Oh, yeah, I remember that." And some of you may be like, "Oh, vaguely." It's okay. But I'm talking about this not because it's like, you must know your math, but because I think this is stuff that you're really going to want to know to do our coming project. The reason I'm mentioning it right now is that, like, if you're looking, as we go through this, you're like, oh yeah, I remember this, no big deal. I'm going to pitch you some practice stuff. If you're like, I know this already, I'm like perfectly comfortable with math, don't sweat it. If you know about yourself, it's like, oh yeah, I really need to practice this. Practice it. I'll send you some practice stuff, okay? I'm not trying to create busy work for you. I'm trying to make the project easier. Okay? So a couple of things about let's talk about triangles. What's that little thing mean there in the corner? It's a right triangle. It's a right triangle. Oops. Means it's a no. Back. Yes. So it's a right triangle. Tell me some things about right triangles. Like, why do we care if something is a right triangle?
I remember, forget what specific section it was, but you could basically use it as like a way of finding distance to where you're standing to where you are.
Useful for measuring distances. Okay, cool. Other things? Yeah.
Trigonometry is all based around right triangles.
Yeah, trigonometry. So trigonometry all based around right triangles. There is some trig you can do with triangles that are not right triangles, but most of the time when we're doing trigonometry, we're using right triangles. Great. What else do you remember about right triangles?
Pythagorean theorem.
Pythagoras, yeah. What is that?
A squared plus b squared equals c squared.
A squared plus b squared equals c squared. What are A and B and C?
C is the hypotenuse.
The C is the hypotenuse, right? So for the purposes of Pythagoras, C is the hypotenuse, and A and B are, what do we call those other things?
One's the base.
Yeah, one's with the base and one's the height, or both of them are legs. I think the thing that's important is you can recognize what's a hypotenuse and what's not a hypotenuse. So Pythagoras is important. That's a pretty good mix. Okay, so let me ask you this. Suppose we have a triangle, and it looks like this. And you know what? I'm gonna get an actual, honest to goodness measurizer instead of making things up. So you're like, all right, that is, I don't know, I'm gonna say that's 60 centimeters. And this is, I would say that's about 24. You've seen this symbol before? What's that symbol?
Theta.
Theta, yeah. It's theta. In math and in science, we often use theta to talk about an angle. If you've ever wondered, like, why do we use this silly symbol? Part of it is that, well, I can't speak for math, but in physics and in astronomy, pretty much all the letters in the alphabet are used up for other things. Like, they all mean, like, you name a letter in the alphabet, and it already has at least one, but probably already 2 or 3 meanings. That's using the Roman alphabet, the one that we use to write English words with. So we're like, what are we going to do for more letters? We use Greek letters. If you're Greek, that's not hard. I had a study partner for a while in school who was Greek, and there was all this stuff that was really obvious to him. I was like, how do you know that? He's like, well, because the Greek word for leg is saphengia. And I'm like, oh. So anyway. Question. Let's say we have this right triangle, and it's got a side that's 24 and a side that's 60. How can we figure out what that angle is? Okay.
Let's use like inverse of one of the trig functions.
Tell me, what do you mean by inverse of one of the trig functions?
Well, I just remember you can use an inverse of like sine or cosine to get an angle.
Yeah. So what are the trig functions? Somebody remind me, yeah?
Sine, cosine.
Yeah, so we go sine, cosine, tangent. And do you folks remember what the mnemonic is for what they mean? SOHCAHTOA, yeah. Oops. SOHCAHTOA. And what are these other letters?
Sine over hypotenuse.
Wait, sine is, what's that?
Opposite
Opposite over
over
hypotenuse.
adjacent.
Adjacent over hypotenuse.
Opposite over adjacent.
Opposite over adjacent. So, which function should we use here to find theta? Right. So here's our angle. Boop. And we're going to go, do we know the hypotenuse? No, we don't know the hypotenuse. We know this. What do we call that guy right there, the 24? That's the opposite. This is the adjacent. So we're going to use something that has opposite and adjacent. That's tangent. Okay. So what we're going to do is we're going to go, the tangent of theta is equal to opposite over hypotenuse. And, oh, thank you. Speak louder. Somebody just murmured because I just made a really obvious, terrible mistake, right? Say it.
Opposite over adjacent.
Adjacent, yeah. I just want to point out, I make lots of mistakes. I'm not trying to, like, there's sometimes people who like made a mistake. I was just testing you. No, I just make a lot of mistakes. I'm like, if I make an obvious mistake in class, it is totally okay. Like, I will not think you're disrespecting me if you're like, yo, Strauss, moron, it's not opposite over hypotenuse. Like, that's okay. I mean, maybe the moron is pushing it a little bit, but you get the idea, right? I'm totally okay with making mistakes. And I actually, like, it's important to me that you folks try, I mean, like, some people are like, I don't want to make a mistake, other people are going to see. Totally understandable, but honestly, the more you're willing to just, like, put stuff out there and be like, oh, that was wrong, like, let's fix it, the better, especially as we go forward and like explore and like try stuff that we don't know. So I'm just putting that out there. So yes, not opposite over hypotenuse. Come on. Yes, opposite over adjacent. And this is why we use erasable things and not permanent markers. Okay, so what we're saying is that the tangent of this angle that we want to know and do not know is equal to, we said the opposite was 20, what did I say? 24 is 24 divided by 60. So you can stick this into a calculator and find out what is 24 over 60. It's like 12 over 30, which is going to be 4 over 10. That's going to be 0.4, I'm pretty sure. Wow. That's kind of interesting. It came out that neatly. So this is going to be about 0.4. So I'm just going to be like, yes, I did that in my head because I'm going to be the tangent of theta is equal to 0.4. Presumably most of the time you're going to need a calculator for that. That's totally fine. So now how do we find out what is theta? Yeah, use a calculator. What are you going to do on the calculator? If you have a calculator handy, I want you to get it out. If you don't, you can use the calculator on your phone. If you aren't familiar with this aspect of the calculator on your phone already, calculator. You don't want to use the calculator holding it like this because it does not know anything about tangents, but somehow when you turn it sideways, your phone gets really smart and it's like, oh yeah, I know what a tangent is. Right? So how do we find out what angle has the tangent of 0.4? So somebody said this right at the beginning.
Oh, the inverse?
Inversed, yeah, inverse. So the way that we do that, like the formal written math here, and honestly, I'm not a math teacher, so I don't care that much about this being that formal, but I'm going to write it that way anyway. I'm going to say that theta is equal to, and there are a couple of different ways of writing inverse tangent. Most calculators, not all, but most calculators write tan with an exponent -1. And if you're looking at your thing and you're like, wait, I only see tangent, I don't see an exponent -1, the way you get that is by pushing the button that says second. Button that says second, and then that should light up, that should convert the tangent button into a tan -1. So what do we get for theta?
0.38.
So theta, to say again?
0.38.
Okay, so we get a calculator. It says 0.38. I'm going to close this up and so 0.38. I'm going to go back here. Does this look like a 0.38 degree angle? No. What's wrong? Is the calculator broken? No. Why did it says 0.38?
It needs to be multiplied by 100.
I got 21.8.
Radian mode. A lot of times in math, they want you in radian mode. So one of the things you want to be careful about when you're doing this is make sure you're in degree mode. So like, and again, if you're using your phone, I'm going to hold this up here for somebody who's watching. If you're using your phone, you want to make sure, like right now, my phone has a little button that says, it has a little thing that says rad right there. If I push the degree button, it goes away. And as long as that, that doesn't say, oops, if it doesn't say rad right there, then you're in degree mode. So this is 0.38. This is 0.38 radians I'm going to put a parenthesis around this because honestly, I don't want to. So I want to take the inverse tan of 0.4 in degrees, and we get?
Like 21.80.
Sounds good to me. 21.8, and I'm going to put the degree symbol on here just to make that. Wow, I would think the highlighter would be like fatter. Is there a way to make it? That's as fat as you get. Okay. I'm gonna just give you another triangle and let you try this on your own for a sec, and let's see how let's try some. So see if you could figure out the angle in each one of those cases. Once you've figured something out, ask the person that, I just made these up, so I do not know. You could be like, Strauss, is that right? I do not know. So talk to them. Let's just see if we can come to agreement about.
What should we round to?
Why don't you round to the 10th of a degree for the moment? Round to the 10th of a degree. While you're, yeah, of course you might. While you're doing this, could I get your moon observations? I'm going to run down and scan them and give them back to you. Try these out. Talk to somebody near you. I'll be right back.
Yeah, you're right. These are all yes. Asia's really so lines.
Oh, yeah, I just saw that.
Right. It's always a good idea when you do this stuff to like do a little gut check. Like if you do this and you end up with 12, you should be like, that does not look like a 12-degree angle. Right? If you do this and you get 94, should you be okay with that?
94.
Yeah, like if you did this out and you get 94, you should not be okay with it. It's not possible to have a right triangle with a 90-degree angle and a 94-degree angle. Right? That should light up for you as like, oh, there's something wrong has happened. Right? Time to go back and figure out what wrong thing happened. Reed, can you talk me through one of these? Pick one.
How about the first one?
Okay.
So the opposite is 10 and the adjacent is 27, so it's tan theta equals 10 over 27, which would be 0.37. And you put that in the calculator, I got 20.3 degrees.
Is that what other people are getting?
Yeah.
20 something, 20.3 degrees? Okay. Anybody have questions about this process? Yes, ma'am.
Well, I did the tan in my calculator, but I don't know how to do like the negative tan.
Okay. Are you using your
Yeah.
phone? Okay.
Like,
Great.
I flipped it over and I did the second tan.
Yeah. So what you do is you put in the number. So type in.
Oops.
That's to clear this out or something like that. You turn off the second thing.
Okay.
Right. And so now go 10 divided by 27. And now you're going to go second. And you're like, I want to take the inverse tan of this. And now you
Oh, so you have like your thing or you
right. You got to have this thing that you're
I
taking.
like took the number and then I typed in the second inverse tan. Good.
Yeah. Make sense?
Yeah.
Okay. So this is an operation you want to be able to do. And I hope in a moment you'll see why. Any other questions about it? Thank you for asking. This business of like, if I'm like, hey, are you good with this? Like, actually, technically speaking, that is actually bad teacher move to be like, is everybody okay with this? Instead of actually trying to figure out, because people are like, I'm not okay, but I'm not going to say anything. Try to say something if you're not okay. We can barrel on. Can we move on? All right. Let's do a story about ancient Greece.
Let's go.
Woo! Ancient Greece. All right. Oh, I'm really not good at this.
Should we take notes on that?
Yes, you're going to want to take notes on this. This is. I mean, I do think it's story time. I do hope you find this interesting. It is also of technical significance. I actually don't know that much about ancient history, but I do know, and these are going to be terrible drawings. Okay. If I had been really prepared, I would have gotten a map or something. But like, you know where the Mediterranean is?
Yeah.
What's the Mediterranean?
It's an ocean.
It's a sea. Great. Where is it?
In the Mediterranean. Between Europe and Africa.
Between Europe and Africa. Awesome. So I'm going to draw like, this is going to be my top of Africa here. Not very good, but that's okay. And then actually it sort of connects up here to what we now call the Middle East. What was one time called the Levant, right? You know, Israel, Syria, Lebanon, blah, 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 Turkey, Greece, a lot of wiggly stuff in islands, some other stuff. You know what comes after Greece? Italy, right? The thing that looks like a boot. I'm just going to draw whatever, right? Blah, blah, blah. Southern France, Spain. Okay. And, oops, maybe I don't want to do it. I'm going to do this in, well, I guess we'll do black. Folks know what this is? Egypt.
Let's go. That was Jack. Oh, let's go Jack.
Do kids still play Risk? Is that game still around?
Yeah, yes.
Yeah, I remember playing, so, you know, I was born in the 1960s, I was through the 70s. We all played Risk. I have no idea why it was a really big thing. I just remember, I can't remember who it was. It was like one of my siblings or one of my neighbors were playing, and it's like, you know, this, it was like, yeah, Egypt. Yeah, Egypt. Okay. So anyway, so here we are. And I can't look at it without thinking Egypt. So then, you know what that is? Nile River. And, oh, maybe. And then right about here, there is a town called Alexandria. And it still exists. Alexandria. Anybody know anything about Alexandria?
I think I should.
Pardon me? You might not. It's totally, you know, you don't get.
They used to have like a big library that burned down thousands of years ago.
Yeah, there was a really big library. There are two things. Again, don't know much ancient history, but there are two. I have two associations with Alexandria. One is like ancient wonders of the world. One of them was the library. One of them was the library at Alexandria. Another was the lighthouse at Alexandria. I guess they had a big lighthouse there, and maybe other people didn't have lighthouses? I don't know. Anyway, so here's Alexandria. It had a big library that was a really big deal. Like if you think about like what was going on 3,000 years ago, there weren't that many books. In fact, there weren't books the way we think of books, but there weren't that many like places where a whole bunch of stuff is written down and you put it all together, maybe by rolling it up or stacking a bunch of papyrus or whatever. And there really were not a lot of places where there were collections of lots of books. So there was this great library in Alexandria, which is kind of amazing because it was a way of bringing a lot of knowledge into one place. And there was a person who was the librarian at Alexandria. And his name was Eratosthenes. Oops, I just spelled that wrong. That's an H, Eratosthenes. Back to the Greek stuff. Yeah, he was Greek. My understand. So the Eratosthenes this is around 200 BCE, and Eratosthenes was the librarian at Alexandria. And the reason that's important is it meant that Eratosthenes had access to like a lot of really important written information. And included in that were sort of records of observations. And in Egypt at the time, people really cared about measuring things that had to do with the sky and the seasons. And one of the reasons was that all, like, Egypt is mostly desert, right? Except for, you know, this area right next to the Nile where once a year the Nile floods and covers it with water. And so it's really, really important to be able to predict when that is going to happen, because it helps you to understand when to plant and when to harvest in order to not get messed up by this flood and also to make good use of the flood. So a lot of, you know, it's not like, it's like, yeah, what were people 2,000 years ago doing, like making a lot of astronomical measurements? They were trying to do anything they could to predict this stuff. And science and religion and magic. So science, religion, magic. It was kind of like all one thing back then. It was like predicting the future, right? And it's easy for us to be like, well, you got a table of the things and you figure it out. Or it might, maybe you do that, but to get people to believe you, you're like, I have this dove and I have cut it open and look at its entrails. That tells me, whatever it takes to get people to believe you. I mean, there were people whose job it was to predict this stuff. It just probably wasn't like, oh yes, I have my court scientist. It was like my court magician. You want people to believe you, you got to do what people are going to improvising. So one of the records that Eratosthenes had was about this town way down here. And this town is currently known as Aswan. But back then, it was either Syene or Cyrene, and honestly, I do not know. I have seen this written both ways. Maybe one is correct and the other is incorrect. Maybe it changed over time. I have no idea. If you see this written either one of these ways, this is what we're talking about. And here's what the record said. The record said that in Syene, so there's a well in Syene. What's a well?
Water.
It's a place where you get water. It holds water. You go deep in the ground, right? It's 2,000 years ago. You don't go to the bathroom and open the tap to get water. You go to a place where you have dug a deep hole where there is water in the bottom. You lower down a bucket, you pull it out, right? So in Syene, there's a well. I know this sounds like, yeah, duh, but I just want to point out, when you dig a well, you don't dig down at an angle, right? Because if you do that, the sides will fall in. So when you dig a well, you dig straight down. This is important. There's a deep well in Syene. Water at the bottom. And that what the records say is that on Midsummer Day, which actually, I don't know what they called it. I'm going to cross that out. Because really what we're talking about is on the solstice. And we'll talk about later about what that is. On the summer solstice. That if you went to the well and you looked down at noon, on the summer solstice, at noon, if you go to the well, and you look down, you'll see a reflection of the sun right down there for not very long. And that tells us something really important. What does that tell? Why is it meaningful that the sun would be visible right down at the bottom?
That means the sun's directly.
The sun is directly overhead. It means the sun must be directly overhead. Like, very, very precisely. It's not just like, oh yeah, it's pretty high in the sky. It's like, in order for it to shine straight down this deep well, it has to be directly overhead. The word that we would use now is the zenith. The sun is at the zenith, the highest point in the sky. So, maybe I can make this prettier. On the summer solstice, at noon, the sun is at zenith. Now, said at the beginning of this course, I think I said it on the first day, and I think this is important, that a lot of astronomy is about measuring things that we can't touch. Right? It's about like, oh, here's that thing, but I can never go there. How will I measure it? This is, in my mind, this is one of those really early examples of that. I think this is amazing. When I think about this, that like, it's so easy to think about history and go like, oh, people were dumb back then. You know, it's like, they thought the Earth was flat. No, they did not think the Earth was flat. They knew that the Earth was round for a variety of reasons. Egyptians knew the Earth was round because if you saw a ship sailing out of port, that you see it, and then it's like, oh, wait a second. I can only see the sail. I can't see the body of the ship anymore. How can that possibly be? Oh, well, it has gone just a little bit below the horizon is here. That's below, and I can see, that if we lived on a flat Earth, an incoming ship wouldn't appear like, oh, flag, then sail, then hull, right? And there's other reasons too. But when I think about this insight that Eratosthenes had, I'm like, whoa. So Eratosthenes used this idea to figure out how to measure the size of the Earth. And here's his reasoning. Here is Eratosthenes' reasoning. So Eratosthenes says, here's the Earth. This is the curve of the Earth. And we know that in Syene, that the sunlight is straight overhead. The sun is far enough away that if we look at different chunks of sunlight, they should not be like, if the sun was like, if it was like that, that would mean like the sun is right here. But the sun is not that close. The sun is very far away. The sun is so far away that these rays should all appear to be pretty much parallel. I'm mentioning that because this is an important geometric assumption. So these sun rays should be all pretty much parallel. Let's see if I can draw kind of parallel lines. So here's Eratosthenes. I still find this mind-blowing. Eratosthenes set up a tall pole in Alexandria, kind of like a flagpole. Set up a tall pole in Alexandria. Now, here's Alexandria. Actually, I'm going to put it right here. Here's Alexandria. Does this pole, if the tall pole point that way? Point toward the sun? No, because a tall pole, if it's straight up and down, has to point perpendicular to the Earth as it is right here. So in Alexandria, he set up a pole. We would now call that pole, we would call it a gnomon. And what he did was he said, if I do that...
Is gnomon spelled with a G?
It is spelled with a G, like gnome. Or, yeah, it's spelled with a G. Gnomon. Yeah.
It's crazy.
It is crazy. And his claim, his insight, is that if you can figure out this angle right here, that you can use that to figure out the size of the Earth. So what he did was he looked at this shadow right here. He looked at this shadow, and he looked at the height of the gnomon, and he figured out what that angle was. And here's why he thought that was valuable. His idea was this. I'm going to draw a line from Syene straight to the center of the Earth. Now I'm going to draw a line from Alexandria straight to the center of the Earth. And I'm going to extend this ray just so that we can see the geometry. All right. I'm going to just highlight this temporarily. If you look at this, oh, come on, technology. If you look at this, and this, and this, you should see something that's familiar to you from geometry. Does that look like a familiar shape in geometry class? Right? Two parallel lines, we got a thing going across them that's called a transverse, doesn't really matter, but what is this angle and this angle? We know something special about those two angles.
They're the same measurement.
The same measurement. Ooh, wow. Well said. They're the same. This angle up here between the light and the pole has the same measurement as this angle here between Alexandria and Syene. They're alternate interior angles. So I'm going to draw this with the same symbol. So that angle there is theta.
Can you post this recording?
I will. I will post this. Not only will I post the recording, I think if I can do this right, I'll post a PDF of all this drawing stuff. So I think it's helpful. Like, different people are different ways. Some people are like, when I take notes, it distracts me and it makes it hard for me to listen. Other people are like, when I take notes, it helps me to remember, even if I never look at the notes. I'm more the latter person. If you're looking at this and like, whoa, if I'm taking notes and not following it, I will post this, okay? So here is Eratosthenes' understanding, is that if I know this angle theta here between Alexandria and Syene, I can tell you what portion of a circle this is, right? So I'm going to say theta divided by 360 degrees. This is how much of a circle is there between Syene and Alexandria, right? It's the portion of a circle, right? If this were 36, if the theta were 36 degrees, that would tell us, oh, from here to here is a tenth of the way around the circle. And so what Eratosthenes realized is that add a little notation here. What portion of a circle? That's this guy right here. And what fraction of a circle are we talking about? He said, well, that is going to be the same thing. Zoom in a little bit. Uh-oh, did I just mess up my drawing somehow? No. Yeah, probably. I did. I moved something.
Fix it.
Fix it? Okay. Yeah, I was hoping undo would fix it. So this distance here from Alexandria to Syene, if you know that distance, then you can figure out the size of the whole Earth. Right? Essentially, what he's saying is this: that theta is to 360 as d is to the circumference of the Earth? I'm going to ask you to figure this out in a moment, but spoiler alert, Eratosthenes was extremely accurate. Let's think about this. This is like 200 BC, and this guy in Egypt figures out how big is the Earth, and he's only off by like 1 or 2%. Here's what Eratosthenes measurements. I'm going to check my notes. I may not have this exactly right. Eratosthenes said the following: Theta, if I recall correctly, was 7.2 degrees, and the distance from the distance we're talking about. And the distance was equal to 5,000 stadia, which was the unit of measurement back then. 5,000 stadia. A stadium, I think, is like 157 meters. So I'm going to write that here. I may have to correct it. 1 stadium equals 157 meters. Okay, we have 8 minutes left in class. I would like you can work solo or you can work with somebody near you. I'd like you to see if you can figure out, according to Eratosthenes, how big was the Earth in stadia. So this would be question number 1. By big, I mean circumference. And that's important because later you'll look this up. And normally, if you Google size of the Earth, they'll probably give you a radius, right? You want to know the circumference. How big is Earth in stadia? I have no idea why they were called stadia. 2. Convert stadia to meters. 3. Look up circumference in meters. Compare. Try this. See if you can use Eratosthenes' method to figure out, according to Eratosthenes, how far around is the Earth. It is totally okay to talk this over with somebody else.
Are you just using the